In December 1972, deep in the Nevada desert, engineers ignited something that shouldn't exist. For 109 minutes, longer than a full movie, a rocket engine roared like a controlled star. Inside, uranium atoms split 93 million times per second, heating hydrogen to diamond vaporizing temperatures. The ground trembled. Radiation sensors screamed. And those watching behind blast shields 2 miles away knew. We just built humanity's bridge to Mars. This wasn't some experimental prototype. The nuclear furnace ran so perfectly, so reliably, that engineers got bored monitoring it. Yet today, this revolution gathers dust in filing cabinets, a ghost haunting NASA's archives. This is the story of NERVA, the engine that could have put your parents on Mars, and why humanity chose to forget we ever built it. Every rocket ever launched fights the same losing battle against physics. Imagine throwing a baseball to the moon with just your arm. No matter your technique, your arm can't generate enough force. That's chemical rockets trying to reach Mars. Magnificent, optimized, but fundamentally limited. The Saturn V's J2 engine, which hurled Apollo to the moon, achieved 421 seconds of specific impulse. That's your rocket's fuel economy. Seconds of thrust per pound of fuel. The Space Shuttle's engine squeezed out 453 seconds. But that's it. That's the wall. Chemical bonds in hydrogen and oxygen store only so much energy. A candy bar compared to what atoms unleash. NASA's 1969 calculations revealed the absurdity. A chemical Mars mission would need to launch 800 metric tons to orbit, 6 Saturn V launches just to wave at Mars. The spacecraft would be 85% fuel, 14% structure, and 1% humans. A massive gas tank with a tiny capsule attached. But atoms don't care about chemical limits. Inside every gram of uranium-235 lurks the energy of 3 tons of coal. While chemical rockets mix liquids, nuclear fission tears apart matter itself. The numbers weren't wishful. They were inevitable. Nuclear thermal rockets promised 825 to 900 seconds of specific impulse, double what chemistry could achieve. It was like your baseball arm could suddenly reach orbit. So, in 1955, while mushroom clouds bloomed over the Pacific, a classified program began in Los Alamos. Tame the atom not to destroy cities, but to reach the stars. Project Rover was born in the same buildings as the atomic bomb. Los Alamos Scientific Laboratory, with Manhattan Project veterans, partnered with the Air Force in 1955. Could we ride nuclear fire to space? Classification was so severe scientists couldn't tell their families what they did. They just disappeared into the desert, returning home exhausted, covered in dust that set off Geiger counters. On July 1st, 1959, humanity crossed a threshold. At Jackass Flats, Nevada test site, the KIWI A reactor went critical. Named after the flightless bird because it would never fly, KIWI did something unprecedented. It used nuclear fission to heat hydrogen and create thrust. For 5 minutes, 70 megawatts of atomic power, enough for 50,000 homes, pushed superheated gas through a nozzle. Los Alamos director Norris Bradbury, watching through periscopes, declared, "We have liberated the atom for propulsion." Then Kennedy pointed at the moon, and everything accelerated. Though Kennedy's 1961 speech focused on beating the Soviets with conventional rockets, NASA Administrator James Webb saw further. In classified congressional testimony, Webb laid out the real vision. The moon is just practice. Mars needs nuclear rockets, or we'll never get there in our lifetimes. Project Rover suddenly had unlimited funding. Make it work, make it safe, make it fly. The desert became humanity's nuclear laboratory. KIWI B4E, tested August 28, 1964, ran for 8 minutes at 937 megawatts, nearly a gigawatt of power. The ground shook so violently cameras 2 miles away needed stabilization. Werner von Braun, builder of the Saturn V, stood slack-jawed. His notes read, "This engine ran 10 times longer than my F1. We are seeing Mars become possible." But the real monster was Phoebus 2A. On June 26, 1968, engineers unleashed 4,082 megawatts of thermal power, over 4 gigawatts, equivalent to 4 nuclear power plants. For 12 minutes, this reactor maintained steel melting temperatures, contained building leveling forces, and did it so smoothly technicians called the test boring. Phoebus wasn't just the most powerful nuclear reactor ever built. It proved atomic rockets had graduated from theory to reality. But building a nuclear reactor was one thing. Making it light enough to fly, safe enough for astronauts, and reliable enough to restart in deep space was an engineering challenge that would define the entire Apollo decade. Harold Finger had an impossible job. As director of the Space Nuclear Propulsion Office, he had to contain 3,000-degree hydrogen, hot enough to turn tungsten into vapor, inside a flying nuclear reactor. His solution, like science fiction, worked like clockwork. Hexagonal fuel elements, pencil-sized, riddled with 19 spaghetti-thin cooling channels. Liquid hydrogen, at minus 253 degrees Celsius, would flow through these channels, stealing heat from the uranium, then blast out the nozzle at velocities that made chemical rockets look lazy. The hydrogen wasn't just propellant. It was coolant, moderator, and radiation shield. This wasn't theoretical. Between 1964 and 1969, engineers tortured over 20 different fuel element designs, subjecting them to temperature swings that would shatter wine glasses. They heated them to 2,500 degrees, cooled them to absolute zero, then heated them again and again. 60 thermal cycles, each a journey from Arctic cold to solar furnace heat. On December 15, 1967, NRX A6 showed what persistence could achieve. The engine ran for 62 minutes straight, over an hour of continuous nuclear thrust. For perspective, the Saturn V's F1 engines burned for 168 seconds. NERVA ran 22 times longer, maintaining power with less than 1% variance. NASA's technical report described it with unusual emotion, unprecedented success in all parameters. But XE Prime was the masterpiece. Tested 3 days after Apollo 11 splashed down, this wasn't just a reactor. It was a complete propulsion system. Turbopumps whirred. Actuators responded. Control systems computed. On December 11, 1969, XE Prime demonstrated 28 restart cycles, throttling from quiet 20% power to full nuclear fury and back. It accumulated 115 minutes of operation, proving nuclear rockets weren't just powerful, they were practical. Program manager Milton Klein told reporters, "XE Prime is not a prototype. This is flight hardware. We could bolt this engine to a rocket tomorrow and fly to Mars. The cost for this revolution? $1.4 billion over 17 years. Less than NASA spent on the Saturn V's paint." NERVA was delivering science fiction capabilities for hardware store prices. By 1969, with XE Prime purring in the desert, NASA drew up blueprints for nuclear Mars ships. Not someday dreams, but engineering documents stamped ready for production. NASA's Integrated Program Plan, delivered to President Nixon on September 15, 1969, wasn't a wish list. It was an instruction manual for conquering the solar system. The 500-page document, buried in archives, detailed nuclear shuttles by 1978, a permanent moon base by 1980, and boots on Mars by November 1982. These were schedules based on existing hardware. The elegance was breathtaking. Replacing the Saturn V's third stage with a NERVA engine would catapult payload capacity to Mars from 30 tons to 75 tons. Imagine moving your house with a pickup versus a semi-trailer. That's the difference NERVA made. Travel time would shrink from 260 days to 180 days, meaning astronauts would absorb 30% less cosmic radiation, arriving healthier, ready to explore. Wernher von Braun became NERVA's prophet. Before Congress in November 1969, the man who sold America on the moon now preached nuclear salvation. Chemical rockets give us flags and footprints on Mars. Nuclear rockets give us cities. His team ran 10,000 computer simulations using real XE prime data. The conclusion: NERVA could deliver a complete Mars base in just 3 launches. The nuclear shuttle concept was even bolder. These atomic workhorses would live in space, ferrying cargo between Earth and Moon like orbital semi-trucks. Boeing showed each shuttle could make 10 round trips before refueling, cutting lunar base resupply costs by 68%. The Moon would become a gas station, Mars a suburb. Then, on January 5, 1973, a single paragraph from the Office of Management and Budget murdered the future. The NERVA program is terminated effective immediately. The reasoning was bureaucratic brutality. All technical objectives have been met or exceeded. The engine is ready for flight development. However, there are no planned missions requiring this capability. Senator William Proxmire, NERVA's executioner, delivered the eulogy. "We're spending millions to reach Mars while poverty exists on Earth. The nation that spent $25 billion reaching the moon couldn't find $200 million to finish the engine that would take us beyond it." NERVA died not from failure, but from succeeding at the wrong moment. But atoms have patience, and physics doesn't forget. Because 50 years later, the nuclear rocket has risen from its grave. And this time, it's brought friends. On May 25, 2019, NASA Administrator Jim Bridenstine stood at Marshall Space Flight Center and spoke words that would have seemed heresy. NASA is going nuclear. Again. The agency unveiled DRACO, demonstration rocket for agile cislunar operations, targeting a nuclear thermal propulsion demonstration by 2027. After half a century of exile, the atom was returning to space. Geopolitics had shifted. In January 2019, China's Chang'e 4 landed on the moon's far side, planting their flag where no one could see it, a metaphor for their ambitions. Their roadmaps showed nuclear cargo ships supporting lunar cities by 2035. Russia announced their nuclear-powered space tug in 2018, claiming it would make chemical rockets as obsolete as sailing ships. The space race had returned. A marathon, not a sprint. Lockheed Martin won the DRACO contract in July 2023, partnering with BWX Technologies, builders of reactors for nuclear submarines. Kirk Shireman, Lockheed's Lunar Exploration VP, made a startling admission: "We're not inventing anything. We're copying homework from 1972. NERVA solved every problem we're facing." The technology resurrection is remarkable. Modern TRISO fuel particles, ceramic spheres the size of poppy seeds, can withstand 1,600 degrees Celsius, solving NERVA's Achilles heel of fuel erosion. Each particle is its own containment vessel, wrapped in carbon and silicon carbide. General Atomics' new reactor design using these particles promises 900+ seconds of specific impulse, double any chemical rocket. Ultra safe. Nuclear Corporation's Michael Eads captures the irony. NERVA engineers with slide rules achieved what we're struggling to match with supercomputers. They'd weep seeing our materials. Carbide composites that laugh at temperature. 3D printing. Computer modeling. We're not surpassing NERVA. We're catching up. Which forces us to confront the equation that keeps physicists awake at night. If NERVA had continued developing for 50 years, where would humanity be today? The mathematics of lost opportunity is suffocating. NERVA was flight-ready in 1972. With continuous development, Mars cargo missions would have been routine by 1990. Permanent Mars bases with 1,000 residents were achievable by 2010. Nuclear propulsion makes asteroid mining profitable. The delta V to reach near-Earth asteroids drops from impossible to trivial. We could have been harvesting trillion-dollar rocks since the 1990s, birthing space industry. The International Space Station could have been built in 3 years with 8 nuclear shuttle flights. O'Neill cylinders, those magnificent space colonies, transform from fantasy to engineering projects when launch costs plummet 80%. We could be living in space cities now. Here's the cruelest calculation. Fusion propulsion. The ultimate cosmic engine requires massive space infrastructure. With nuclear thermal rockets providing cheap access to orbit, fusion experiments could have proceeded in space since the 1980s. We might today be launching interstellar probes instead of struggling to return to the moon. So, we're left staring at NERVA's ghost. A perfect engine that worked too well for its own good. Somewhere in the Nevada desert, Test Cell C stands like a concrete cathedral. The rails that carried NERVA engines are rust orange but strong enough to hold another rocket. The control room sits empty, except for tumbleweeds and memories. These aren't monuments to failure. They're monuments to a future we built, tested, perfected, and then abandoned. NERVA proved something profound. Barriers to human expansion aren't technological. They're psychological. We didn't abandon nuclear rockets because they failed. We abandoned them because we succeeded and then lost the courage to use our success. The engine that ran perfectly for 109 minutes in 1972 could have been pushing spacecraft to Mars by 1975. Instead, it was dismantled, studied, and filed away like a letter from a future we decided not to visit. Today, as we resurrect this technology with DRACO, we're not pioneering. We're remembering. The bitter comedy is that modern nuclear thermal rockets, for all their supercomputers and miracle materials, are still trying to match what engineers achieved with slide rules and raw determination in the Nevada desert. Stan Borowski, NERVA's keeper of the flame, offers the perfect epitaph. Every Mars study eventually rediscovers NERVA. It's not whether we'll use nuclear propulsion. It's whether we'll admit we need what we already perfected. What do you think would be different today if NERVA had powered our space program for the last 50 years? Would we be walking on Mars? Mining asteroids? Or would we have found new ways to abandon our dreams? And now that we're bringing nuclear propulsion back from the dead, will we have the courage to use it this time? Or will we bury it again? Let me know your thoughts below. And tell me which abandoned space technology deserves resurrection next. If you want more stories of futures we threw away, hit subscribe. Until next time, keep looking up and remember, somewhere in a filing cabinet, the blueprints for our cosmic future are waiting. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.